So now we're going to go back and revisit the idea of differentiability, what it means for a function to be differentiable, to have a derivative, and all that. When we did this last time, we looked at a graph and picked out places where it was not differentiable, didn't have a derivative because it either wasn't continuous or had a sharp turn or had a vertical tangent. But now we're going to deal with, here's a formula for a function. How can we analyze if that function presented with a formula is differentiable or not? So here's our rule. A function f of x is differentiable at a particular x value, x equals c, if a function f of x is differentiable at x equals c if, first of all, it's got to be continuous. If it's continuous at x equals c. And how do we know if a function is continuous? Well, we have that three-part limit definition. If the limit as x approaches c from the left of our function equals f of c equals the limit as x approaches c from the right of my function. This is nothing new. This is exactly our definition of continuous from chapter 1. A function is continuous at x equals c if the limit as x approaches c from the left of the function equals f of c equals the limit as x approaches c from the right of our function. But then we have to make sure there aren't any sharp turns, aren't any vertical tangents. Our derivative must also be continuous at x equals c. Its derivative is continuous at x equals c, which means the limit as x approaches c from the left of f prime of x is going to equal, actually I'm not going to say f prime of c, we'll talk about that later. It's just going to be a two-part equation. The limit as x approaches c from the left of f prime of x equals the limit as x approaches c from the right of f prime of x. And basically, if they're equal, we'll make one piece of the piecewise function an equal two-part, but otherwise f prime would be undefined and our piecewise function wouldn't be defined there. We're not going to worry too much about this, but we have those two things being equal. Take a moment and make sure you get that definition copied down. I'll pause. So the first one I want to look at is the function f of x, which equals x squared plus 3 when x is greater than or equal to 1, and 6 minus x when x is less than 1. Is that function differentiable at x equals 1? Is that function differentiable at x equals 1? F of x equals 2x squared plus 3 when x is greater than or equal to 1, and 6 minus x when x is less than 1. Two things I have to check. First, is it continuous? Which means I need to go find the limit as x approaches 1 from the left of my function. I have to find f of 1, and I have to find the limit as x approaches 1 from the right of my function. Take a moment, go find those three things, and then we'll reach a conclusion based on that. Well, the limit as x approaches 1 from the left of my function is the limit as x approaches 1 from the left of 6 minus x. That's 6 minus 1, we're going to get 5. F of 1, that's defined by the top part, 2 times 1 squared plus 3, that's 5. And the limit as x approaches 1 from the right of the function is the limit as x approaches 1 from the right of 2x squared plus 3, That's going to be 2 times 1 squared plus 3. That's going to be 5. Limit from the left equals the value of the function there equals the limit from the right. I think we're good. Yes, we're continuous. Didn't ask you to justify it. If you were asked to justify, you'd have to say because the limit is x approaches 1 from the left of f of x equals f of 1 equals good enough for us right now. But that's only half the battle. That's what we would have done in Unit 1. I didn't ask if it was continuous. I asked if it was differentiable. We know we're continuous, and now we need to see if our derivative is continuous. If the derivative isn't continuous, that would mean I could have a sharp turn, or I could have a vertical tangent. I need to go, first of all, find f prime of x. We haven't yet found the derivative of a piecewise function, but it's really easy. All we have to do is the derivative of the top piece and the derivative of the bottom piece. We'll keep our same inequalities, except I'm just going to do away with the equal part for right now. I'm going to say I get 4x when x is greater than 1. I'm going to get negative 1 when x is less than 1. And if it ends up having a continuous derivative, then I'll just put an equal to part on one of these two things. Otherwise, if the derivative is not continuous, the derivative won't be defined there, so it wouldn't even make sense to talk about one of them as being equal. The next thing we have to go do is the limit as x approaches 1 from the left of f prime of x, and the limit as x approaches 1 from the right of f prime of x. Well, take a moment and go find those. I'm just doing the limit of that constant function, so I'm going to get negative 1. Limit as x approaches 1 from the 1 from the right of 4x is going to equal 4 times 1 is going to equal 4. Those things are not equal, so no. Our derivative is not continuous, which means our function, f of x, is not differentiable at x equals 1. My function was continuous, but the derivative wasn't continuous, so I wasn't differentiable at x equals 1. If you're looking at the graph, it would look something like this. And you can see, yeah, there's a pretty sharp turn over there. Actually, I know exactly what's going on. It's changing from a slope of negative 1 to a slope of positive 4 right over there, because that's what I got with my limits over there of my derivative. Nope, not differentiable at x equals 1. So, to figure out if a function is differentiable somewhere, you first have to make sure it's continuous there. That's like what we did in Chapter 1. Then you find the derivative of both pieces and all that stuff, and then see if the derivative is continuous at x equals c. Let's try another one. Let's take a look at the function f of x, which equals x squared plus 1 when x is less than or equal to 2, and 4x minus 3 when x is greater than 2. F of x equals x squared plus 1 when x is less than or equal to 2, and 4x minus 3 when x is greater than 2. The first thing I need you to do is check to see if it's continuous. So take a moment, find those three things, your two limits and your one f value, and make a conclusion based on that. So I'm going to get 5 for my limit from the left. F of 2 is defined the same way, so 2 squared plus 1, that's 5. And from the right, I'm going to do the limit as x approaches 2 from the right of f of x. 4 times 2 minus 3, 8 minus 3, I'm going to get 5. Yep, I'm continuous. Not good enough, though. Now I need to check to see if the derivative is continuous. Go back so we can see the original function. Derivative, continuous. Well, I'm going to go find f prime of x. You take a moment, go find f prime of x. I'll wait. Let's see, should be 2x when x is less than 2. Should be 4 when x is greater than 2. I'm not going to put an equal sign on yet, because if my derivative isn't continuous, then my derivative doesn't exist at x equals 2. Otherwise, if it is continuous, then I'll just stick an equal sign on one of those parts. Again, we're not going to worry too much about this. And now, you need to go check the limit as x approaches 2 from the left of f prime of x, and you also need to go check the limit as x approaches 2 from the right of f prime of x. Go check both of those. Getting 4 for that one. Over here, the limit as x approaches 2 from the right of the constant 4 is 4. Those things are equal. Looks like my derivative is continuous. My original function was continuous. So yes, f of x is differentiable at x equals 2. And actually, because the original function was continuous everywhere else, and the derivative is continuous everywhere else, I'm differentiable everywhere. The graph of this one looks like this. So smooth you can't even really tell that at x equals 2 you're changing from one function to another function, but this is a parabola, and that's a line segment. Or that's a line, rather.